morning. So today I am going to go ahead and record our lesson for section 4.1 kind of in advance, just in case we have some issues with school on Monday. So we're going to start with a warm-up. What I'd like you to do is go ahead, I'm going to walk you, read this to you, then I want you to pause it, think about it for a minute, and then unpause and we'll figure out the answer. So suppose I take a sheet of paper and I tear it in half. Then I take the two halves and I put them one on top of the other. So now I have a stack with two sheets of paper. If I take that stack and tear it down the middle and then stack those, now I have a stack with 4 sheets of paper. And I would continue to do this. So suppose I continue to do this 20 times. How tall do you think the final stack would be? So pause for a minute, think to yourself, I'm going to tear a sheet of paper in half and stack it 20 times. Let's think about how tall the stack would be. All right, so let's first figure out how many sheets of paper we're talking about, right? So let's see if I can get my screen to work. Come on. Oh, there we go. Okay. So let's just call X the number of tears, and then we'll call Y the number of sheets of paper that we have stacked in our stack. So if we have 1 tear, we now have 2 sheets of paper. After 2 tears, we have 4 sheets of paper. After 3 tears, we have 8 sheets of paper. And it keeps doubling from there because we keep tearing it in half and stacking it on top of itself. So if we were to continue this, how would we figure out how many sheets of paper we'd have after 20 tears? Well, let's think about these numbers for a second. This number 2 is the same thing as 2 to the first. And 4 is the same thing as 2 squared. And 8 is the same thing as 2 cubed. And 16 is 2 to the fourth. And if you think about it, it makes sense because what are we doing to go from one term to the next? Each time we're multiplying by 2. So each of these numbers becomes 2 with a higher exponent, and these are all powers of 2. So after 20 tears, it would make sense that we would have 2 to the 20th sheets of paper. 2 to the 20th, if I grab my calculator, is 1,048,576 sheets of paper. That's with 20 tears. And that's the power of exponential functions. They look like they're just kind of growing a little bit as you move along, but once you start kind of hitting the higher, even just medium to high numbers, all of a sudden they just start shooting up really, really fast. And that's the power of exponential functions. Now with 1,000,000 sheets of paper, how tall is the actual stack? I'm going to just go with a ream of 500 sheets is around 2 inches high. So if 500 sheets of paper is about 2 inches thick, then if I divide my 1,000,000 by 500 and multiply by 2, that tells me that my stack would be roughly 4,194 inches high. How many feet is that? If I divide it by 12, so it's around 349, let's just round to 350 feet. Around 350 feet high. That's a pretty high stack from 1 sheet of paper, right? If you want to challenge yourself a little bit, you might want to actually see if you can figure out what is the area of each sheet once you have torn the paper 20 times. But we're not going to get into that right now. All right. So today we're doing section 4.1, which is on exponential functions. We're going to learn what the basic parent function is. We're going to learn how to transform them a little bit. We're going to learn growth and decay, and we're going to do a little bit of modeling. Oh, and we're going to learn point ratio form. Okay. So the first example we're going to start with is cars. We've talked about this before. Most cars go down in value. As soon as you drive them off the lot, the price drops. So let's talk about a car that was originally $14,000. So we're going to start time with year 0. So if I think of it as, if my time, this is time in years, and this is my, let's call it V for value of the car. At year 0, our car is $14,000. After 1 year, the car has depreciated by 1/5. If the car has depreciated by 1/5, that means it has lost 1/5 of its value. So what is the value of the car? The value of the car is 4/5 of that original price. 1/5 was lost, 4/5 remain. So we would do 14,000 times 4/5. So I got to set down my coffee so I can get this number. So 14,000 times 4/5. So after a year, our car is worth $11,200. After 2 years, what would we do? We would take the 11,200 and multiply that by 4/5. So it would be the 11,200, kind of thinking recursively for a little bit, times 4/5. So we get times 4/5, and we end up with $8,960. After 3 years, multiply by 4/5 again, and we end up with $7,168. Now, the question is, what is the value after 2.5 years? You can't just take the 2 and the 3 and average them. It doesn't work like that. It's not a linear function. It doesn't have a constant rate of growth, so you can't just average these two values. We need an actual function that represents this decay so that we can plug any number in and find the value of the car. So here's our function. Let's think about this. So we started, I'll put V for value. Okay, so we started with a value of $14,000, right? And then each year we multiply times 4/5. So after the first year, we would have 14,000 times 4/5 to the first. After the second year, we would have 14,000 times 4/5 times 4/5, or 14,000 times 4/5 to the second. In general, we're going to have 14,000, oh, I called it variable t, 14,000 times 4/5 to the t. Normally it's x. I called it t for this problem, so we're going to stick with t. So I have 14,000 times 4/5 to the t. Let's make sure this works. If t is 0, remember that any number to the 0 power is 1. So v of 0 would be 14,000 times 4/5 to the 0. This right here is 1. So v of 0 is 14,000, which makes sense. That's our initial value of our car. If we wanted v of 2.5, which is what question A asks for, it would be 14,000 times 4/5 to the 2.5. For this, you just plug it in your calculator, 14,000 times 4/5. Remember that caret button? So when I'm typing in my calculator, this would be 14,000 times 4/5, and then I'd hit the caret button, and then I'd put 2.5. You don't really need parentheses for 2.5, but anyway. All right, so what is v of 2.5? I'm trouble getting that extended. There we go. So v of 2.5 is around 8,000 $14.07, kind of rounding a little bit. So that would be the value of our car after 2.5 years. When is this automobile worth half of its original value? So the original value is $14,000. So for part B, we would set 7,000 equal to our 14,000 times 4/5 to the t. So when we divide by 14,000, what we end up here is a half. And so a half equals 4/5 to the t. Now, there's a way to solve this using logs. Let's see, I'm going to pause for a second, see to make sure I teach you the right way to solve. All right, I just wanted to consult with another teacher, make sure that I didn't teach you an incorrect method or a method that I shouldn't be teaching you. So because we aren't going to do logs for a few weeks, what we're going to do instead to solve this equation is just graph both sides. So in y1, you can let y1 equal a half, and then in your y2, put in 4/5 to the x. And then what happens, so if I put 1/2 in my y1, and then I put 4/5 to the x in my y2, and then I'm going to do a standard, let's see. Oh, I'm going to have, let's see, I'm going to try a standard window and see what I get. There's my half, and down comes my exponential function. So what you get is you get a graph that looks like this. So you have your y equals a half kind of coming along, that's a horizontal line, and then you get your exponential decay kind of going down like that. And you're looking for this point of intersection, and the way you get there is you go to calc, which is second trace. So you go calc, and then choice 5 is intersect. So I think we've done this before, but let's just do it again anyway. Then you hit enter on your first curve, just hit enter, enter, and then if it asks you for a guess, just hit enter again. Enter, enter, enter. And what it tells us then is that our x is around 3.106 when our y is a half. So it takes about 3.106 years for the car to lose half its value, which is pretty quick. So, two main types of exponential functions. We have decay and we have growth. The names are pretty self-explanatory. Decay means that your function, the value is going down. So if you look at your decay graph, it's decreasing as you go from left to right. And then your exponential growth, of course, is increasing as you go from left to right. So decay, as x decreases, it says your y, it's weird to say as x decreases. Let's just talk as x increases, because we always go from left to right on graphs. So as x increases, y decreases. And here, as x increases, y increases. So how do you know if a graph is decay or growth? It's all about the base right here. This number right here, that b. If the b is between 0 and 1, the graph is decay. So if the b is less than 1, your graph is going to be a decay graph. Because you're multiplying by a number less than 1 every time, so your number is going to get smaller. If your b is greater than 1, then you're going to have a growth graph. Because, of course, your number, when you multiply by a number bigger than 1, then the numbers get bigger. So the other thing, a little bit of vocabulary here. So this is the general form of an exponential is a times b to the x. B has to be positive. If b is negative, it's just nonsense. Your graph's just going to flip back and forth. So b has to be positive, and b is the rate of growth. So if you're in our last problem, our rate of growth was 4/5. So technically it could be growth or decay. So since our rate was 4/5, our B was 4/5 because each time from year to year we were multiplying by 4/5. So that's your rate of growth. By the way, A, let's see, I think it's on a different screen. Oh, no, right here. A is your y-intercept. A is your initial value. It's the value when your time is 0 or when your x value is 0. So if you have A times B to the x, A is going to be the value when your x is 0. And then there's also, of course, going to be a value like some sort of a half. When you have half of A, then the amount of time it takes you to have half of A is called the half-life. So once our A drops to half of its value, then this time right here, the time that it takes is called the half-life. And then here's our starting A. If A doubles, then the time it takes for A to double is called the doubling time. You're going to see half-life more than doubling time, but that's okay. All right, moving on. Feel free to pause if you need to write some of this down. End behavior. So we haven't really talked a lot about end behavior, but we have talked about infinity. So let's talk about this notation. This x this is supposed to be an arrow, so I'm going to kind of fill this in. What this says is, as x approaches, I can spell R-O-A-C-H-E-S, approaches infinity. As x approaches infinity, what does y approach? So where is infinity? Infinity for your x values is way out here. Think as far out here as you can possibly go. So this graph is never going to go negative. You're never going to take a positive number, raise it to a power, and make it negative. It's never going to go negative, but it is going to get really close to 0. So as x approaches infinity, our y values are getting closer and closer to 0. So think as we move to the right, what's happening to our y values? They're going to 0. In the other direction, so as x approaches negative infinity, so now we're moving this way, as x goes way out here, think negative infinity, not -1, negative infinity, what is happening to our y's? What are the y's approaching? The y's are approaching infinity. They're just going to keep going up forever to the left. Some people call this the right end behavior and the left end behavior. What happens to the y values as we move to the right, and what happens to the y values as we move to the left? On a growth graph, it's exactly the opposite. So if we're talking about exponential growth, as x approaches infinity, fill in these arrows. So as x approaches infinity, as we move out this way, what's happening to our y's? The y's are pointing to infinity. As x approaches negative infinity, so we move out this way, what's happening to our y's? The y's are approaching 0. And we'll do more with end behavior throughout the course, but end behavior is really talking about what do the y values approach at the far ends of the function, the far left end and the far right end. Okay, so the functions g of x equals 1/2 times 2 to the x and 2 to the x minus 1 are transformations of the parent function 2 to the x. Describe the graph of the parent function, then describe the graph of the transformations. So if we think of y equals 2 to the x, then our a that we've been talking about is 1, because there's just an invisible number out here, and our b is 2. That's our rate of growth. So we have a y-intercept of 1, and then each time from there we're multiplying by 2. So now we have times 2 is 2, times 2 is 4, times 2 is 8, which is like up here. And so as we move to the right, we multiply by 2. If we're moving to the left, we're dividing by 2. So here we would have 1/2 and 1/4 and 1/8 and it would just get like super, super small towards the x-axis. So our graph of y equals 2 to the x looks like that. And you can ask yourself, plug in some numbers and see. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. You can always make a table, right? I'm going to go ahead and show that as well. So 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. Okay. Let's talk about transformations. This first transformation means that we're going to dilate by a factor of 1/2. It's on the outside, so we're multiplying all of our y values by a 1/2. So if we multiply all of our y values by a 1/2, this 1 becomes a 1/2, and this 2 becomes a 1, and 4 becomes a 2, and 8 becomes a 4, and then 2 to the 4th, which is 16, would become an 8, and then all of these would get like really, really small, and you end up same general shape. It's still an exponential growth graph, but now everything has been multiplied by a 1/2. So 1/2 times 2 to the x. All right, so I'm going to label that. So that's y equals 1/2 times 2 to the x. All right, if I have y equals 2 to the x minus 1, I'm subtracting 1 from my x, which means I'm going to translate the graph to the right by 1. By the way, I didn't write this here. This is already done. Dilate by a factor of 1/2. All right, so if I take my original parent function, that's the red graph, and I translate to the right 1, whoa, let's see what happens. Move to the right, move to the right, move to the right. What? That is crazy. It's like I'm right on top. I'm right on top of my 1/2 times 2 to the x. So, anyway, so there's a reason for that. I don't know if I should get into it right now. I think we get into that in just a few minutes when we get into our point ratio functions. So let's move on. These are graphs, though. So just from this screen, the main thing to know is that transformations, the exact same transformations you learned in Chapter 3, still apply. When you add or subtract to the x, it's a horizontal translation. If you add or subtract to the outside, to the y value, it's a vertical translation. Multiplying is a dilation factor, and then, of course, a negative up front would reflect it, right, over the x-axis. Or a negative inside would reflect over the y. Okay, so consider the equation y equals 10 times 0.4 to the x. Find the y-intercept. The y-intercept is that number right here. It's that 10 that's in front. So, and then of course, if we wanted our rate of growth, our growth rate would be 0.4. I'm just going to write that down. So our growth, actually this is we call it the growth rate. I'm going to call it the decay rate because it's less than 1, so let's call it decay rate. Rate of decay. All right, find another point on the curve to write an equivalent equation. We're going to call this point ratio form. How do we find another point on the curve? Plug in any value you want for x. So for example, if x equals 1, then y equals 10 times 0.4 to the first, which is 4. So we have the point 1, 4. Oops, there. All right, how do we use this then to write a new equation? I'm going to give you a model here. So point ratio form. So you have y equals, it's kind of like, do you remember point slope? When we were in point slope form equation of a line, you needed just a point and a slope. When you do point ratio form, you need a point and a ratio. That ratio is the same thing as the decay rate. So that's your ratio. All right, so you have y1 times your ratio to the x minus x1. x1, y1, that's your point. So x1, y1 is any point on the graph. So an equivalent equation would be y equals the y value, which is 4, times our ratio, which is 0.4, raised to the x minus the x value of the point, which is 1. And there's an equivalent equation. Use algebra to prove that your two equations are equal. Well, let's see. So if I have y equals 10 times 0.4 to the x, I'm going to write them out here, equals 10 times 0.4 to the x, and I have y equals 4 times 0.4 to the x minus 1. Okay, so let's see. I'm going to set these equal to each other. So I have 10 times 0.4 to the x equals 4 times 0.4 to the x minus 1. So this is the same, x minus, if I raise to the x, let's see. Four is the same thing, hang on one second. Okay, there's two different ways to go. I'm kind of going back and forth on which way I want to show you. One way would be to say that this 0.4 to the x minus 1 is equal to 0.4 to the x times 0.4 to the negative first. Because when you multiply, you add your exponents. So you end up with, I'm going to move this up here, 4 times 0.4 to the x times 1 over 0.4. But 4 divided by 0.4 is 10. This uses some algebra that you haven't quite learned yet. So I'm not, if you didn't pick up on this, don't worry about it too much. We'll learn this more when we get into properties of exponents. We could also do it by breaking this side up, but I couldn't decide which side would be easier for you to pick up on. But if you don't pick up on this, that's okay. We're going to do more when we get into properties of exponents. All right, use your calculator to prove that your two equations are equal. Much easier to do. So you can just put y1 equals your 10 times 0.4 to the x, and in y2 you can put in your 4 times 0.4 to the x minus 1, and then when you graph them both, what you're going to end up with is the exact same equation right on top of itself. So you can either check by checking the graph to see that it goes right on top of itself. You could do a trace on several numbers to see if they have the same ordered pairs for both graphs. Or you can look at your table and you'll see that all the y values are the same for both equations. All right, 2 to the x and 1/2 to the x. Can you shift these functions left, right, up, and down? Absolutely. If our parent function is 2 to the x, so we start at 1, because remember there's an invisible 1 in front of there, and then 2 to the first is 2, 4, 8, right, 1/2, 1/4. And we get y equals 2 to the x. If we wanted to shift this graph up, we could say, hey, how about, let's let a new, I'm going to call it a new function. How about 2 to the x plus 3? Then this graph would be shifted up by 3. So every single point, you just add 3. So we'd add 3. And then 4, we'd add 3, and you'd end up, and then here, 1/2, we'd add 3, and something like this. So if you notice, this first graph flattens out at 0. The second graph now flattens out at 3. All right, and then the same thing would happen for 1/2 to the x. If you add 3, you would shift the graph up 3. Let's go ahead and take 1/2 to the x. So I'm going to graph 1/2 to the x, and we'll shift that one left or right. So if I have 1/2, so we start at 1, because remember, again, there's an invisible 1 in front. That's your y-intercept. 1/2 to the first is a half. A half squared is a fourth, and an eighth, and so forth. What gets confusing is 1/2 to the negative first. We haven't really learned negative exponents yet. Negative exponents mean take the reciprocal and then apply the exponent. So 1/2 to the first is the same thing as 2 to the first. Or 1/2 to the negative first is the same as 2 to the first. So 1/2 to the negative first is 2. 1/2 to the negative second is the same as 2 squared, and it's 4. So when we get into our negative exponents, when we do our properties of exponents, it'll be easier for you to learn. But that's our 1/2 to the x. And then say we wanted to shift this, how about 3 to the left? So let's call our new function g, and let's say it's 1/2 to the x plus 3. So then that would be shifts left 3. So we end up with a graph. So I move my 0 over here, 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 and go to here. Something like that. And then I accomplish a shift left. So remember, when you're adding or subtracting to the y value, that's an up or down. When you're adding or subtracting to the x value, that's a left or right, and it does the opposite, just like we did in chapter 3. All right, I think this is our last example. Let's just walk through this. Ginny Weasley puts 3,000 galleons into a savings account at Gringotts. The chart shows the growth of Ginny's money for the first few years it's there. So how do we find her rate of growth? To find the rate of growth, you can take any y value and divide it by the previous y value. If you did it to any pair, you would get the same number. So our rate of growth is 3081 divided by 3,000. 381. Okay, and this is equal to 1.027. All right, so that's her rate of growth. What is the value of her savings account after 7 years? So we're just going to assume that it is compounding annually, since we're only given time in years. So we're not given time in months or quarters or anything like that. So the value after 7 years, let's write our equation. So our dollar amount, we didn't give variables. I'm going to call that x and that y. So our y equals our initial value times our growth rate raised to the x, raised to the time. So if I want the amount in the savings account after 7 years, I would have 3,000 times 1.027 to the 7th. And she would have, after 7 years, around $3,615.05. All right, when does the account double in its original value? So the original value is 3,000. So we're looking for where it equals 6,000. 6,000 equals 3,000 times 1.027 to the x. So then if I divide both sides by 3,000, I get 2 equals 1.027 to the x. How do I solve this? For now, we're just going to graph. Let y1 equals 2, let y2 equal 1.027 to the x. And so I'm going to do the same thing. Let me clear my calculator. So I have y1 equals 2, and y2 equals 1.027 to the x. And I graph. There's my 2. There's my exponential. So my window wasn't big enough. So here's my 2. my 1.027 to the x, which started down here and went up, this value wasn't on the screen, so I have to change my window. So I'm going to change my x max from 10 to, let's just say 30, and see if that is far out enough for it to cross. Just barely, just barely. So let's go ahead and do a calc. And I'm going to do my intersect. So calc, intersect, enter, enter, enter. And this value is around 26.02. So when does the count double? It doubles after about 26.02 years. Is how long it would take to double. If it stayed in the account and she didn't put any more money in. That's it, guys. So, think about how are increasing exponential functions different from decreasing. Remember that has to do with your rate of growth being less than 1 or greater than 1. Why is b never negative? Because if you take a negative number and raise it to an exponent, every time the exponent is odd, the value would be negative, and every time it's even, it'd be positive. So you'd have a graph that would be flip-flopping back and forth over the x-axis, and it wouldn't really tell you much. All right, have a good day.